Loose sea of electrons are available to carry heat and electricity easily through the metal, making them excellent conductors of heat and electricity. The non-fixed nature of the bonds means that atoms can slide past each other but will stay bonded, making it easy to bend or hammer metals into shape without breaking them.
These ionic compounds have very high melting points and are brittle because of their 3D giant ionic lattice structure. The strong electrostatic attractions holding the 3D lattice structure in place mean that a lot of energy is required to overcome these attractions. When we apply a force, it breaks the regular repeating pattern of oppositely charged ions, causing ions with like charges to come close to one another. The ensuing repulsion breaks the lattice structure. Most ionic compounds are soluble in water. In water, an ionic compound can dissociate into its ions. So when we dissolve sodium chloride, it will dissociate into sodium and chloride ions. An ionic compound dissolved in water can conduct electricity. This is another key property of ionic compounds. This is made possible due to the presence of free-floating ions. Following on the same idea, molten ionic compounds can also conduct electricity. The lattice structure is broken at high temperatures, and so the ions become free-floating.
Another property to note is that simple molecular substances don't conduct electricity, because there are no free electrons, and the molecules themselves have no electric charge. You'll see this point again and again in chemistry. In order to conduct electricity or heat, substances have to have some electrons or ions that are free to move about. In diamond, each of the carbon atoms is covalently bonded to 4 other carbon atoms, which is the maximum number of bonds that carbon can make. This forms a regular 3D pattern. As each of these covalent bonds is really strong, it will take loads of energy to break them. And so diamond itself is very strong and has a really high melting point. However, it doesn't conduct electricity, because it has no free electrons or ions that can move around. Now let's compare these features of diamond to those of graphite. First, each carbon in graphite is bonded to only 3 other carbon atoms, rather than 4 in the case of diamond. Second, the atoms are arranged into hexagons that together form large flat sheets, which are then arranged on top of one another to form lots of layers. However, these individual layers are only held together weakly, as there are no covalent bonds between them. This means that they're free to slide over one another, which makes graphite relatively soft when compared to diamond. That said, graphite still has a very high melting point, because the individual layers are strongly held together with covalent bonds. Now, do you remember how earlier we said that carbon atoms can make 4 covalent bonds each, but in graphite they only make 3? Well, that means that each carbon atom in graphite has 1 spare electron that it's not using in bonding. Instead, this electron becomes delocalized, which basically means that it's free to move around. And all of these free electrons allow the graphite to conduct electricity and heat.